Welcome to the lecture. In this lecture series, we start from the third module, and today we are discussing the geometrical representation of signals. Assume that I have a point. Okay, I have a point, and I want to represent this point in space. Now, what we'll do in a simpler method, we will just draw a line through the point. Okay, and I'll mark the origin somewhere here, and this distance represents my point P, and this is the one-dimensional representation of that point. Let this be X. I can have a different representation, that is, I have the point P here. I can have two-dimensional representation where I have X and Y axis, two axes, and this is the component of P in X axis, and this is the component of P in Y axis. Again, I can have a three-dimensional representation where I have another axis Z. Let X, Y, and Z axis, and this is my point. So this is Py, and this is Px, and this is Pz, and this is my point P. And this is generally called the Cartesian space, where I have a point in space and I am representing that in a three-dimensional space. So I have three axes or three basis vectors. Okay, the first basis is X, or we don't have order, so we have three bases, X, Y, and Z, or basis vectors X, Y, and Z. You should note one point here, that this X, Y, and Z carry some property, or a major property, which is called orthonormality, or simply orthogonality. What do that mean? That is, you have the axes X, Y, and Z. By orthogonality, we mean that X, Y, and Z are orthogonal to each other, that is, they are at 90 degree. That is in a geometrical terms, that is X, Y, and Z are at 90 degree. Okay, X, Y, and Z are at 90 degree. What do that mean in vector terms, or in vector algebra? If two vectors are, two vectors are at 90 degree, which implies that they are orthogonal. Or their inner product, or the dot product inner product is 0. That is, inner product between X and Y is 0, inner product between X and Z is 0, and inner product between Y and Z is 0. Okay, this is what orthogonality means. Orthogonality means if two vectors are orthogonal, their inner product is 0. Okay, so in the Cartesian space we have three vectors. They are mutually perpendicular, or they are orthogonal, or their inner product 0. Now assume a different scenario where I have a sine wave. Okay, a sine wave, it's some amplitude A, some time period t, and a phase phi. I represent this sine wave as y is equal to e sine omega t plus phi. This is phi 1, let it be called as phi 1, and this is some a1. Okay, and my sine wave is actually y1 is a1 sine omega 1 t plus phi 1. That is, a sine wave is represented by three variables: the amplitude A, frequency omega, and phase phi. We can give different values for these three variables and obtain different sine waves. Note that A, omega, and phi, they do not have anything in common. They do not have anything in common. In a sense, you can say they are orthogonal. See, x, y, and z are orthogonal. So x doesn't have any component in y. If you y doesn't have any component in x, and y doesn't have any component in z as well. Assume a situation like this. This is a vector A, and this is a vector B. Here, A has a component in B. This is that component. How to obtain this component? The component of A in the direction of B is nothing but A dot B, or inner product between A and B. But if A and B are at 90 degrees, they do not have any component in B. So that is the beauty of orthogonality. So if the vectors are orthogonal, they do not have anything in common. Now here, A, omega, and phi are different quantities, and they do not have anything in common, and you can say they are orthogonal. If that is the case, you can represent A, omega, and phi like this. This is A, this represents A, this represents omega, and this represents phi. Now a point here will have a value in a value in phi, and a value in omega. Okay, it means this point P is a sine wave with an amplitude, let it be A1, let's be phi 1, and this is omega 1. So this is a sine wave with amplitude A1, sine omega, that is frequency omega 1, and phase phi 1. This is P1, okay, so let me call this as P1. This is P1. This is a sine wave. This point is actually a sine wave. It's the point in this particular space, or you can say this is a space of sine waves of different amplitudes or frequencies and phase, or you can say this is the space of all possible sine waves. That is, you take any sine wave that exists in the world, and that can be represented as a point in this particular space. So any sine wave can be represented as a point in this particular space. So this space, this three-dimensional space, is a space of all possible sine waves. Now consider a different case, a different scenario, where I have three sine waves. Let's call the first sine wave as x1 of t is sine 2 pi 50t. Okay, that is sine wave with frequency 50 Hz. x2 of t is sine 2 pi 100t, sine wave with 100 Hz, frequency 100 Hz. And x3 of t is a sine wave with frequency 150 Hz. Okay, so these are the sine waves that I have. Assume that I am adding them together. So the signal y1 of t is x1 of t plus x2 of t plus x3 of t. So I have the simulations here. These are the sine waves. So the first sine wave is 50 Hz sine wave, the second one is 100 Hz, and the other one is 150 Hz, and I have added them together, and I obtained a different kind of wave. It's not a sine wave, some noisy kind of thing. Now the point here is that if these three sine waves are orthogonal to each other, which they are actually, that we will discuss in the end. If they are orthogonal, these three sine waves are orthogonal, I can represent each sine wave as a different direction, like this. See, I have a sine wave x1 here, x2 which is orthogonal to x1, and x3, or x1, x2 and x3. I have three sine waves, x1, x2 and x3. Then my signal y1 will be a point in the space constituted by x1 to x3. Y1 is constructed by x1 and x2 and x3 by simply adding them without any scaling. So these sine waves were the sine wave with unit amplitude. They are the sine waves with unit amplitude. So I have taken one time x1 and one time x2 and one time x3 and added them together to form the signal y1. This is my signal y1 in terms of x1 to x3, and I have represented that as a point in space, or I have represented the signal y1 geometrically. The point here is that x1 to x3 are orthogonal signal, they are orthogonal to each other. Then I can represent them as different directions. Okay, different vectors or different directions or different bases. I call them bases. Okay, the first basis, second basis and third basis, they are orthogonal to each other, and now any combination of them will be a point constituted by these three vectors. We can have different kind of signals y is created by this x1 to x3. You can scale them with different values and add them together to form different signal. For example, I have a signal here. Here I have scaled y by x1 by 2, x2 by 3 and x3 by 4. That is, so this is the equation. y2 is 2 times x1 plus 3 times x2 plus 4 times x3. Now that point is somewhere in that space, x1, x2 and x3. 2 times x1, 3 times x2 and 4 times x3. Okay, this is my point, my signal y2 of t. Okay, I have represented y2 in the same space. So this is the concept of signal space representation or geometrical representation of signals, where I represent signal as a combination of different signals, and these signals x1 to x3 are my bases. So I represent my signal as a linear combination of my basic or basis signals. That's what we do in geometrical representation of signals. Now, what is the use of this this thing? Suppose that I want to transmit this signal y2. I want to transmit this signal. Okay, transmitter and receiver. So if I want to transmit this signal, I need to transmit each and every point of the signal. So I need to transmit the signal itself, right? Each and every point in the signal need to be transmitted to the receiver. If the transmitter and receiver agrees on the basis, that means the transmitter says that I have a signal, I am going to transmit a signal which lies in the space constituted by the bases x1, x2 and x3. This x1, x2, x3 is known by the transmitter as well as receiver. Okay, the transmitter and receiver knows x1, x2 and x3. Okay, then in that case you don't have to transmit this entire signal to the receiver. You just need to transmit the components the signal y has in x1, x2 and x3. Say this is the signal I am going to transmit, so I don't have to transmit the signal, but say this is my signal, then I just need to transmit px1, px2 and px3, 3 different values. Say p is represented by px1, px2 and px3. Instead of transmitting this whole signal, I just need to transmit this vector p. 3 values, 3 simple values that will generate the signal, which is very much easier. I need to transmit infinite points in the signal if I am directly transmitting this signal to the receiver, but here I just need to transmit 3 points. But the transmitter and receiver know what are the basis functions or basis signals x1, x2 and x3. Then what transmitter receiver do? It simply scales x1 by px1 and x2 by px2 and x3 by px3, add them together to form the signal. So if I am transmitting a different signal, the p will be different. P x1, x2, x3 will be different. It will be corresponding to that particular signal. Then receiver will construct a different signal. Say this is p2. So it will have different components in these bases. Then those components will be transmitted. P2 will be transmitted, and that will be generated in the receiver side. So this is the advantage of signal space representation. So we can formally define now the signal space a representation, or we can say like this. Suppose I have m, okay, m energy signals. I have m energy signals represented as Si of t, where I is from 1 to m. I have m energy signals and n basis functions. Signals and functions we use interchangeably, okay. M basis functions, phi 1 of t, phi 2 of t, etc. up to phi n of t, provided m is greater than or equal to n, or n is less than or equal to m. Okay, now I can represent the signal Si of t in terms of these basis functions. I can represent the signal Si of t as sigma Sij phi j of t, where j moving from 1 to n. That is, this is nothing but Si is my signal, Si1 phi 1 of t plus Si2 phi 2 of t plus etc. up to Sin phi n of t. This is what this summation is. So what I am doing here is that I take the contribution of my signal Si in the basis phi 1 and multiply my basis by that value, then take the contribution of my signal Si in the second basis phi 2 and multiply my basis by that, and like that find the contribution of my signal in each of the bases and then multiply by the bases and add them together. That will give you the signal Si, as we have done previously. In this case we simply we had basis functions x1 to x3 and we added them together with these things, with these scaling factors 2, 3 and 4, and obtained a signal y2. Now this is actually synthesis. We combine the signals to form a new signal, synthesis. Now suppose you are given with this signal. So you are given with this signal. You are given this signal and you are asked to find what is the contribution of the first basis to the signal, contribution of second basis to the signal, third basis to the signal. That is, actually we know that it is 2, 3 and 4, but we don't know because you have written the equation here, you know, but if you are given with this signal, how can you find out the contribution of each signal in this each basis in this signal? That is pretty simple, right? Because we know how to find the contribution of each axis to a vector. For example, if you have x1, x2, x3, these three axes, and how to find this one, contribution of this point in this axis, contribution of this point in this axis, how to find that? just find the inner product. Or else let's go to the first example. Okay, so this example, so how to find px. Let's write an equation, something like this. Let's say p is 4x plus 5y plus 6, is it? So to find, this is the contribution in x-axis, this is the contribution y-axis, this is the contribution in z-axis. Okay, now to find px, px from this equation you can actually note that it is 4, but actually analytically how you find is you simply find the inner product between p and x. That will give you px. Here p and x, find the inner product, you will get 4, right? Inner product means you need to just you need to take the corresponding values and multiply and add them together. Say we have two vectors, 4x plus 5y plus 6z and x plus y plus z, p1 p2. Just need if you want to find the inner product, what you do, find the component of x in each, multiply, find the component of y in each, multiply, find the component of z in each, multiply, and add them together. Here 4 into 1 plus 5 into 1 plus 6 into 1, that will be the inner product. Similarly, to find the inner product between p and x, we just need to multiply with px, and x is actually normalized, so it will have 1 in the direction of x, so 4 will be the value px. To find py, you need to find the inner product between p and y, similarly x, so that's how you get px is equal to 4 and py is equal to 5 and pz equal to 6. Now again, going back to our example, to find SI1, SI2 and SI, or find Sij, how to find Sij? That's the question. Sij is nothing but the inner product between Si of t and phi j of t. So you want to find the component of Si in the basis phi j. Just find the inner product, that will give you the component. And in the case of inner functions, the inner product is calculated as this. Say suppose these are periodic functions, so take a period 0 to t, Si of t phi j of t dt. This is the inner product between the functions Si and phi j. So what does it do? Here what you are doing is you simply multiply the functions point wise, multiply them point wise, okay, then you will get some other function, integrate that function over a period, that will give you the inner product. So this is the basic idea of signal space representation, where you have n basis functions and m signals, where m is greater than or equal to n, and you represent each of the signal in terms of bases by this equation. To find the component of your particular signal in each of the bases, you just need to find the inner product between your signal and the basis. Okay, now as I said earlier, we just need to verify that sine waves that we used earlier are orthogonal to each other. Okay, these are the sine waves, okay, x1, x2 and x3 that we use, 50 Hz, 100 Hz and 150 Hz. They have a relation in between because they are a multiple of basic frequency, 50 Hz 2 times 50 hertz 100 hertz, 3 times 50 hertz is 150 hertz. So because of this particular um, um, relationship, they are orthogonal to each other. So orthogonality means what? If you multiply them together and integrate, they should give 0. I have multiplied them together point wise, so x1, x2 and x3 are multiplied together point wise and formed this function. Okay, these functions are multiplied together to form this function. In MATLAB you can do it as well. Now I have a function like this. If you carefully examine, you can see that suppose you draw an axis here, in axis here. Okay, one thing you can find is that it is kind of periodic. See, it has a particular period. See, it has a particular period. This is repetitive. Say if you analyze this section, it is repetitive. Again, analyze this section, it is repetitive. Okay, it's repetitive. Now, and in that itself, if you carefully examine, you can see that the area in the positive side and the area in the negative side are equal to each other. Now if you integrate it over a period, it will give you 0, and that means if you integrate the entire signal, that will give you 0. This is because it has a positive and negative sides equal. So if you integrate them together, that will give 0. This is just a verification of that orthogonality property of periodically harmonically related sine waves. You can do it in MATLAB and verify yourself. Okay, so this is a general introduction to the signal space analysis or geometrical representation of signals, and we will see Gram-Schmidt orthogonalization procedure in the next lecture, where we actually construct basis functions from the signals that are given. So if you have a set of m signals and we construct basis function, n basis functions out of the m signals itself, that's what Gram-Schmidt orthogonalization procedure do, and we will see that in the next lecture. Thank you.